Okay, let's plot the logistic functions a couple of different ways to see the various things we can do with this logistic regression. Okay, so let me just walk through this program. So this little piece, all it does is plot the standard logistic function. So really from minus infinity to plus infinity, but of course we're just plotting from minus 10 to 10. And this is the what I call the standard logistic function or the prototypical logistic function. It starts slowly from 0 at minus infinity and then slowly goes up to 1 at plus infinity. It reaches the value of 0.5 when z equals 0. Okay, so that's the standard logistic function, and then let's look at what happens when we transform it, transform the underlying variable, say using a linear transformation. So let's say now the input variable is x list, then you say b naught plus b1 x equals z, and then now we can plot x versus z. Of course, x versus z is just going to be, or z versus x is just going to be a linear function. But we can also plot g versus x, right? So we can compute g of z, this new z, which is a linear transform version of our input. G of z is going to be, of course, the logistic function, but g of x, or g as a function of x, is going to be a shifted and scaled, but in terms of the slopes, logistic function. So let me run this thing. Okay, so when you plot z versus x, because x and z are linearly related, you just have the straight line. It doesn't pass through the origin. It's just passes through the y point equal to 4, I guess. That's the y-intercept, and then has a slope of 2. That's this thing, and then the logistic is this, and you notice that it's not anymore centered about 0. It's going to be centered about minus b naught over b1. It's centered about the x value where z equals 0. Okay, when z equals 0, this point, that's exactly when the probability g becomes 0.5. Okay, z equals 0 corresponds to h, or g equals 0.5. It's where the transition happens from 0 to 1, or probability less than 0.5 to probability greater than 0.5. Okay, so that's if you have a linear relationship between z and x. What if we have a quadratic relationship? So let's try that. So x is the same, the input x is the same, and then you try to, instead of saying z equals b naught plus b1x, you say z equals b naught plus b1x plus b2 x squared. Let me just make that plus and then make this minus. Okay, it's just some random quadratic expression. And let me first run this piece. Let me close this. Let me run this piece. Okay, so z is a quadratic function of x. And then let me run this piece, which now computes g of z. In other words, applies the logistic function to z and then plots g of z versus x. Okay. Okay, so this is what we get. Interesting, right? So instead of being this sort of a simple logistic function, g of z is still, if you plot g with respect to z, it will still be the simple logistic function. But because we're plotting g or h with respect to x, it looks like this. Now, why is that? Recall that when z is basically less than 0, if you look at this function, right? So this is how g is related to z, and z is related to x in this manner. So when x is negative, very negative, Well, z is very, very, very negative. Um, when z is very negative, g is basically 0. And then here, when x is very positive, z is again negative. So g is again 0. So basically, when x is very negative or when x is positive, z is negative and you get h is basically 0. And then for a brief period, z becomes greater than 0 here. And when z is substantially greater than 0, g of z or h of x becomes close to 1, this part, right? So by having essentially a nonlinear transformation between x and z, the input x and z, this variable, you can actually have, you can approximate sort of probability distributions with this kind of flavor as well, where the pieces where your output is 0 is not necessarily contiguous or what's called simply connected. Okay, so you can have these piecemeal thing, and you will notice that you will have to use this idea in one of the homework problems. Okay. Okay, so that's in one dimension. Okay, and of course, by making this expression more complicated, maybe more polynomial, you can have multiple ups and downs for the logistic function. Okay, so I guess we'll leave it at that. Let's look at some 2D data. So what does 2D data mean, or data with two inputs, one output? So this thing that we did is one input, one output, right? X is the input, Y is the output, or G of Z is the prediction of the output. Now let's look at the case where you have P and Q as two different inputs, and Y is the output. This I'm just actually generating some data. You don't have to pay attention to detail how I'm generating the data. You can take a look at the program, but let me just generate it and plot it. Okay, here's P, here's Q. Oops. Okay, here's P, here's Q, and then here's Y, the output, right? So for different values of P and Q, which it looks like varies from -20 to +20 in both directions, Y takes a value of 0 or 1. Okay, let me rotate this thing to see what that looks like. Okay, so Y is 0 or 1. In other words, there is a binary sort of assignment of output depending on P and Q, and we would like to figure out, is there a sort of condition, how can we approximate, first of all, data like this, and maybe more simply, is there a boundary that separates these two kinds of outputs? Okay, so to visualize that better, or differently at least, um, just focusing on the P and Q inputs, you can visualize this kind of data in this manner. All we have done is, here's the code for this. When y list equals 1, we plot p list of y list equals 1, q list of y list equals 1 with a r, a red circle. And then when y list equal to 0, we plot p and q with a blue cross. And that's what the data looks like. So instead of plotting this in 3D, we plotted this in 2D. Okay. Now, of course, it looks like there is actually a straight line in these two dimensions that separates these two sets of data, where y equals 0 versus y equals 1. Okay, so hold that thought. So in logistic regression, we would like to, for instance, find the straight line, okay, relating P and Q. And similarly, if you have many more variables, P, Q, R, S, T, many more input variables, and then you have an output variable of Y, a corresponding problem would be, in this many-dimensional input space, we want to find a plane that separates the data that has Y equals 0 and Y equals 1. Okay, that plane would be called a separating hyperplane or a decision boundary. Okay. We'll talk about that again. Okay, so that's if, so this would be called linearly separable because the data can be separated by a line or a plane, linear. And then let me actually, here is an example where the data is separable but not linearly separable. Okay, so let me just run this whole thing. Okay, so here's P, Q, and then Y, and I just created some data that has the flavor of, for certain values of P and Q, Y equals 0, and then for other values of P and Q, Y equals 1. And and then if you plot it in this kind of visualization, you notice that the values of P and Q that give you Y equals 0 is actually sort of sitting inside an ellipse, maybe. And then the values of P and Q that result in Y equals 1 are these red dots, okay? We will see motivation for like an example where something like this naturally arises. In fact, for material failure problems, things like this will naturally arise, where when the stress states is within a particular region, you don't fail, and then when the stress states, which is high dimensional, is outside of that region, the material fails. Okay. Okay. So here, like I said, it's not linearly separable. It's separable by an ellipse, or in this case, a quadratic expression, right? An ellipse is basically a quadratic expression. A plane or a line is a linear expression, right? Okay. So I just wanted to show data that looks like this to motivate the next thing. So we would want to approximate or find conditions for separating data that looks like this. Okay. Okay, so let's now look at how we would approximate data that looks like this, or what kind of functions. I'm now going to do the same thing that we did for one dimensions. Again, we have this function g of z. It's the same function, exactly the same function g as a function of z, which is this standard logistic function, right? 1 over 1 plus e power minus z is that function, right? So if I right click this, open this, you get this function. That's what this function is. F or g, more precisely, is basically 1 over 1 plus e power z. I put a dot divide because in these programs, I'm actually inputting z as a whole vector, and I would like these operations to be performed for every value of that vector array or matrix, and then give me the corresponding g matrix or array for every value of z. So I'm putting dot divide, okay? Because we will be evaluating g for very large values of z, very small values of z, this part is just to make sure that the output never exceeds 1 or doesn't go below 1 for any value of z. Of course, this function essentially makes sure that this will be the case, but because occasionally numerical procedures can have very small errors, maybe at the 10 power minus 16th level, I want to absolutely make sure that the output of this function is between 0 and 1. And that's what this thing does. This basically makes sure that if g is greater than or equal to 1, g is 1, less than or equal to 0, g is 0. And when it's between 0 and 1, it's the same g as here. Okay. Anyway, so that's the logistic function we all know and like, this standard thing. Now let's now apply the same one-dimensional logistic function g of z for many dimensional problems, in particular two-dimensional problems. But 2 is just a special case. You can have 20 dimensions, you can have 200 dimensions, you can have 200,000 dimensions, and we will do a 200 dimensional problem in the next lecture. Okay, so but let's now look at two-dimensional for a moment. So here I'm now trying to plot a function. I'm saying p is between minus 10 and 10, q is between minus 10 and 10. and then I define this thing called p grid and q grid. Let me actually show you what that looks like. So let me run this piece. So p list is just this 0 to 10, q list is 0 to 10, and then p grid um, is basically goes from not 0 to 10, I guess minus 10 to 10. Basically goes from minus 10 to 10 on the x-axis, minus 10 to 10 on the y-axis. And what this allows, if you plot p grid comma q grid, let me just close all, plot p grid comma q grid. So it's actually a grid of points. P list is just this list of points. Q is just a list of points. P grid, Q grid basically gives a list of points that is all possible combinations of P grid and P list and Q list. Okay, so let me plot this thing. Let me plot this all in blue. Okay, so what is this? We've just plotted P grid comma Q grid. So P grid comma Q grid is basically every possible grid point in this 10 by 10 grid. Okay, so now if we actually evaluate, let's say, some other function on every possible grid point on this grid, you will be able to plot like surface plots and things like that. So it's using this mesh grid allows you to basically mesh a two-dimensional square or a rectangle. Basically mesh grid basically does a grid on a two-dimensional rectangle. Okay, so you start from a list on this p-axis, list on this q-axis. Actually this is the p-axis, is the q-axis to be more precise, if you think of p grid and q grid. But the way we plotted it, certainly this is p and this is q. In any case, p grid and q grid, if you take the I comma jth element, will give you some point on this grid. Okay, anyway, so we have this n by n or 30 by 30, 900 points for p and q. Now for those 900 points we compute z. First we say z is a linear function of p and q, so z is b naught plus b1p plus b2q, and then we just do a surface plot, surf p grid, q grid, z value grid. So let me run that. And because z is a linear function of p and q, p, q, z, you have this linear function. Okay. Now what we are going to do is take the z, compute g of z, namely apply the logistic function to this z, right? So the logistic function is still that thing. When you apply this to z, when z becomes greater than 0, g of z will become close to 1. When z is substantially less than 0, g of z will go to 0. So let's look at that. Okay, so this is the logistic function applied to this plane. Let me just rotate this to show you what this looks like. Okay, so it's the same range, p, I should have said x instead of saying the same. Right, so when z, this quantity z is less than 0, g of z, actually this should be g of z. I keep messing this up. This is c, this is g of z. Okay, so okay, p, q, g of z. So when p and q combine to give you a z, this is g of z. When p and q combine to give you a z that is less than 0, it gives a g of z that is basically close to 0, right? And then when p and q combine to give you a z that is substantially greater than 0, g of z gives you close to 1. Okay, so we've essentially now we are now able to predict or try to approximate uh, data with two inputs and then one binary output. And by choosing B naught, B1, and B2, we can figure out like what the correct separating hyperplane is or the decision boundary is. Okay, so by generalizing this expression to two input dimensions, we can approximate functions that have one output and two inputs, for instance. Okay, so that's if you have a linear function here relating the inputs and the z variable. Now let's actually look at a nonlinear function. I just made up a nonlinear function here, which is some constant plus some other constant times p minus 1 whole square, some other constant q minus 2 whole square, something, right? Notice that this almost looks like the equation of a circle. Actually, it's the equation of an ellipse. Some constant, uh, this is the center of the ellipse, 1 comma 2, and so on. In any case, let's just run this thing. Let me close this. Okay, so this is a quadratic expression. And of course, a quadratic expression looks like this bowl because for large values of p and q, you go for like the function keeps increasing. And the function is less than 0. Z is less than 0 for some brief period of time, and then greater than 0 for most periods of most values of p and q. So let's apply the logistic function to z and see what that looks like, right? So p and q gets transformed to z, which can take any value, or at least these values. Now g of z will take values between 0 and 1, and let's just look at what that does. Okay, so this is kind of a neat looking picture. Hopefully, let me turn this to show you how what that looks like. Okay, so that's what that function looks like. It's equal to 1 when z just dips below 0. So z dips below 0 ever so slightly, actually in the region that looks elliptical. And then z is much greater than 0 for most of the values of p and q. So when z dips below 0, you have g of z equal to close to 0. And then when z is substantially greater than 0, g of z gets close to 1, right? So this is the function. This is the output of this function. So this actually allows us to approximate data that looks like this, right? So data that looks like this, we just found a function that actually can approximate data that looks like this. We actually need to put a negative sign because here the inside of the ellipse is 0, the outside of the ellipse is 1, whereas for this function that we created, the inside is 0, the outside is 1. And to actually change that whole thing, if you change all these parameters, it looks like this, right? So where inside the ellipse, g of z becomes close to 1, outside the ellipse, g of z becomes close to 0. Okay, so you can literally try to find basically b naught, b1, maybe this number can also be unknowns, b3, b4 maybe. You can write a general quadratic expression. I wrote a very specific quadratic expression, but you can, at least in a specific form, you can write it in a more general form to approximate other things like hyperbolas and so on. This actually allows only ellipses, but if you write a general quadratic expression, you can allow the separating boundaries to be hyperbolas, circles, straight lines, in fact, are special cases of hyperbolas. Okay, so, and then we can make it cubic. I don't know, let me just make this cubic and see what that looks like. Leave this a square. You start getting more complex separating planes. Okay, for some values of p and q, g is 1, and for other values of p and q, g is 0, and the separating boundary are basically these cubic curves. The separating boundary actually can be gotten by setting whatever this expression is to 0. If you set this expression to 0, that's actually the separating boundary for all these things. Okay, so that's important to realize. Whatever expression of the inputs is equal to z, if you set z equal to 0, that's actually the separating boundary. Okay. Let's switch to nodes and we'll see some more examples in a minute.